Tonight's journey follows relativistic jets, narrow beams launched near black holes. They cut across intergalactic space and reshape their surroundings in silence. Expect calm checkpoints, magnetic structure that keeps a beam tight, bright knots that mark gentle compressions, wide lobes and soft rims that store energy for ages. If this kind of slow science story helps the mind unwind, please like the video and subscribe for more long-form cosmic sleep documentaries. Now, let the scene rein. Let the light thin. Let the jet become a quiet line across the dark. A black hole can appear perfectly dark, yet a narrow jet can shine far beyond its host galaxy. The jet stays focused for about 1 million light years, like a single sunbeam that holds together across a wide valley of fog. In that region, the beam is not the decoration. It is a map of how gravity, motion and magnetism organize matter at the edge of a deep well. The first scene is simple and slow. A faint galaxy halo hangs like thin smoke. From its center, 2 slender streaks extend in opposite directions. Each streak looks edged and clean near its core. The brightness fades outward in a long gradient. The jet does not fill space like a cloud. It draws a line through it. A small unlock arrives early. A jet is not made of light alone. It is a flow of plasma, which means gas with separated charges. Plasma follows magnetic fields more readily than neutral gas. That single idea explains why the beam can keep its shape. It also explains why the beam can keep a memory of its origin. The scale shift is gentle but dramatic. The launch region is smaller than a solar system. The visible beam can reach far past the disk of a galaxy. Distance stretches the story. Cause and effect do not feel connected at first. Yet the beam carries the imprint of a tiny region into a volume that can span clusters of galaxies. A second scene forms at the center. A bright disk circles the darkness. The disk is thin and layered. It brightens inward. Near the inner edge, the light rises steeply. Then it ends at a sharp boundary. That boundary is not a wall. It is the place where stable orbits give way to plunging paths. The rim looks like a luminous ring beside a missing center. Another unlock settles into place. Jets begin where motion is ordered. The accretion disk provides that order. Gas in the disk rotates in the same sense. It shears in thin layers. Friction and turbulence heat it. Rotation also stretches magnetic fields into long arcs. Those arcs are invisible. Their effects are not. The main concepts remain few. Plasma is one. Magnetic field structure is another. Collimation is the third. Collimation means the narrowing and guiding of a flow. A wide outflow becomes a thin column and stays thin. The jet base is not seen directly. The reason is a quiet limit of observation. From far away, the launch region is too small in angle to separate. Its light blends into a single bright point. Surrounding glow from the disk also blurs the contrast. A signal would carry mixed information from many zones. The jet must be understood from patterns farther out. A third scene appears along the inner rim. A faint funnel region opens above the disk. Density drops there. The glow becomes more transparent. Magnetic field lines arch upward from the disk surface. They bend into a narrow bundle. The bundle curves in a subtle helix. The helix is not a decoration. It is a geometry that can guide charged particles. A small payoff follows from that geometry. Magnetic fields can act like tensioned threads. When twisted, they resist sideways expansion. That resistance can pinch the plasma toward the axis. At the same time, pressure inside the jet pushes outward. Balance sets the jet width. The jet becomes a corridor held by forces that pull and push. Along the jet wall, the brightness often softens. A faint sheath appears. It is cooler and slower. It cushions the core. The core stays straighter. The sheath takes the first contact with surrounding gas. The boundary is where waves grow. It is also where the beam can fray. The everyday analogy stays in the natural world. A narrow waterfall can keep a coherent core as it falls. Spray forms at the edges. The center stays faster and denser. The jet behaves similarly. A faster core can be wrapped by a slower sheath. Mixing happens at the boundary. It is limited and layered. A fourth scene develops farther from the centre. The jet shows knots. Brightness rises in compact patches. Between knots, the beam dims but remains present. The edges stay sharper than a simple plume would allow. The beam also shows slight bends. The bends are smooth. They suggest that the surrounding medium is not uniform. Another payoff lands without strain. Those knots can be understood as changes in speed. Faster plasma catches slower plasma. Compression forms, heat rises locally, radiation increases. The knots are a record of uneven feeding near the base. The beam turns a hidden rhythm into a visible chain. The limit of intuition arrives next. Speed in a jet can be close to the speed of light. Common experience fails there. Time and distance no longer feel separate. Brightness can be boosted by motion. Even the order of events can appear shuffled. A moving pattern can seem to jump ahead. That is a projection effect shaped by a light travel time. A fifth scene widens the view again. The jet crosses the galaxy halo and enters thinner space. The background glow drops. The beam remains narrow. Its brightness declines more slowly than the surrounding light. The jet seems to cut a channel through a faint haze. A further unlock comes from the channel idea. The jet is not only a feature inside the galaxy, it is an interaction with what surrounds it. The beam pushes on ambient gas. Ambient gas pushes back. That exchange shapes the beam. It can also heat large volumes over long times. The physical details stay concrete. The jet has a core and an edge. The edge can show a shear layer. Brightness can peak on the axis and fall outward. The disk has a bright inner rim and a darker outer gradient. A shadowed center sits where light vanishes. The closing view returns to the paired beams. Two opposite directions suggest a central engine with a preferred axis. The axis is set by rotation and field. The next steps move closer to the rim. They follow the rotation that powers order. They track how fields tighten and guide the flow. Near the center, a thin ring of light gathers into a clean, bright boundary. That boundary marks the last region where a steady orbit can persist. The first view is quiet and close. A flat disk glows in layers. Its color warms inward. Its surface shows a faint texture. The texture looks like shallow ripples on compacted sand. Light behaves as if the disk is both a road and a furnace. Gas circles while it slowly drifts inward. The drift is gentle compared with the rotation. The key is not speed alone. The key is what rotation refuses to give up. Angular momentum means rotation that resists falling straight inward. A simple picture helps. A nautilus shell grows in chambers. Each chamber keeps the same spiral form. The size changes while the pattern remains. In that region, the disk keeps a spiral story. Matter moves inward while preserving a memory of turning. A small unlock arrives. Inward motion requires losing angular momentum. Heat and turbulence provide the loss. The disk does not slide inward as a whole sheet. It shifts through layers. One layer hands rotation to another. That handoff turns motion into heat. The heat raises brightness. The brightness climbs toward the inner rim. The next scene sits closer to the dark center. The rim sharpens. The glow ends over a short radial span. Beyond it, the disk becomes thin and dim. The dimness is not a lack of material alone. The dimness is a change in path. Stable circles stop being stable. The innermost stable orbit is the smallest circular track that lasts. Inside that track, small disturbances do not settle. They grow. Paths tighten. Then they plunge. The rim is not a wall. It is a threshold in the geometry of gravity. Another unlock settles into place. The inner rim becomes a natural anchor for structure. The disk density rises there. The temperature rises there. Magnetic fields also concentrate there. Field lines thread the disk like fine fibers. Rotation winds them. Winding stores energy in the field. The field then pushes back on the plasma. This mutual grip shapes the funnel above the disk. The funnel is less dense. It offers an easier channel for outflow. The physical details remain clear. The disk has a top and a bottom surface. Each surface can carry a magnetized skin. The skin can peel upward into arcs. The arcs lean toward an axis. Along that axis, pressure and magnetic tension balance into a narrow corridor. A soft scale shift follows. The rim can sit only a few times farther out than the horizon edge. About 3 times the horizon radius is a useful scale. It is like 3 nested rings inside a single spiral shell, yet the effects of that ring can be written across distances that dwarf a galaxy. The next scene draws attention to gradients. Brightness rises inward, density rises inward. The change is not uniform, it steepens near the rim. That steepening matters. A steep gradient can stabilize an outflow channel. It can also amplify small fluctuations. The disk can flicker. The flicker can seed patterns in the jet base. A payoff arrives with calm certainty. A jet does not begin as a distant spear. It begins as a local decision of forces near the rim. If the field is ordered, plasma follows the order. If the field is tangled, plasma leaks sideways. The narrow beam seen far away depends on this early order. Another visual anchor appears a short distance above the rim. The funnel looks like a dim cone. Its sides are outlined by faint glow. The glow is brighter along the rim-facing edges. The cone points into darkness. It is bordered by a thin sheath. The sheath is slightly brighter than the interior. That brightness hints at a boundary layer where plasma rubs and heats. The boundary layer is not a sharp line. It is a narrow band. It has thickness. It has a gradient in speed. It has a gradient in temperature. Those gradients are the places where instabilities can grow. A limit of observation enters gently. The inner rim itself is too small to resolve directly at most distances. Its size on the sky collapses into a point. Light from the rim also blends with light from the inner disk. A signal would carry only an average. The rim is inferred from patterns. Broadening of spectral features suggests fast motion. Timing changes suggest orbital scales. These inferences depend on models. They also depend on assumptions about disk thickness and emission. The limit is clear. Geometry is reconstructed indirectly. Another unlock comes from that limitation. Indirect evidence still constrains the boundary. A stable orbit leaves a repeated timing scale. A plunging region leaves a smoother fade. The disk brightness profile leaves a characteristic steepening. These clues allow the rim to be placed within a narrow range. The disk then becomes a measuring stick. It ties the unseen boundary to the visible outflow. The final scene widens slightly. The disk surface looks calmer outward, the inner region looks more restless. The rim remains the clean divide between order and plunge. From that divide, the axis of the jet becomes more than a line. It becomes the extension of a rotating system into surrounding space. The next step follows rotation itself. It moves from disk motion to the deeper twist of space-time near a spinning black hole. A spinning black hole does not shine. Yet, its rotation can shape the light and plasma nearby. In that region, spin turns space-time into a gentle conveyor that can lend energy to an outflow. The scene tightens to the darkest center. The disk inner rim stays bright and thin. Above it, the funnel looks clearer and more hollow. The darkness at the center has a smooth edge. The edge is not a surface. It is a boundary where escape becomes impossible. Around that boundary, starlight bends into arcs. The arcs appear as a soft ring-like curve. The curve is uneven in brightness. One side looks slightly more intense. The imbalance hints at motion and geometry. A small unlock arrives early. Rotation is not confined to matter alone. Rotation can be written into the surrounding space-time. Frame dragging means spinning space-time carries nearby paths along. The definition stays simple. Frame dragging means space-time rotation nudges nearby motion into the same swirl. The image is quiet and precise. Lines of flow above the disk no longer point straight. They curve, they coil, they align toward an axis. The everyday analogy stays natural. A rotating storm over warm ocean can pull surrounding air into a spiral band. The storm does not touch distant air directly. Pressure and rotation organize it. In that region, space-time plays the role of the organizing swirl. The scale shift follows with calm contrast. The horizon boundary can be smaller than a planetary orbit. The influence of the spin can extend through the inner disk and into the base of a jet. From a very small region, a preference in direction emerges. The jet then carries that preference far outward. Another visual anchor slows the pace. The funnel above the disk looks like a dim corridor. Its sides are traced by faint emission. The emission forms a layered gradient. It is brighter near the base. It fades with height. The corridor is not empty. A thin plasma fills it. The plasma is not evenly distributed. It forms a core and a sheath. The core stays most aligned with the axis. The sheath clings to the funnel wall. A payoff settles in place. A jet needs an axis that stays stable. Spin provides a stable axis. Magnetic fields can then use that axis like a guideline. A second concept enters with care. The ergosphere is a region where space-time forces co-rotation. Ergosphere means a zone where no object stays still. The zone sits outside the horizon. It has a smooth outer boundary. That boundary depends on latitude around the hole. It bulges outward near the equator. It tightens near the poles. The shape is not spherical, it is slightly squashed. It resembles a soft oval around a darker core. A clear physical detail emerges from that shape. The outer edge of the ergosphere is a surface of changing possibility. Inside it, a path that tries to remain fixed is dragged forward. The dragging is not friction, it is geometry. Another unlock arrives without strain. Energy can be extracted from rotation because the ergosphere changes what counts as energy. Some trajectories can carry negative energy relative to faraway space. When such material falls inward, the black hole loses a small amount of rotational energy. The outflow can gain that energy. This exchange does not require any mechanical contact. It requires only that plasma and fields tap the rotating geometry. The main number arrives and stays gentle. Signals and changes near the base can unfold on about 1 hour like a weather front shifting across a calm sea. That timescale sets a rhythm in brightness. It can also set a rhythm in knot formation farther out. The comparison stays everyday and quiet. The hour scale beat is slow enough to imagine. The consequence is large. Tiny variations near the center can become bright patches across vast distances. A new scene appears in slow motion. A bundle of magnetic field lines rises from the inner disk. The bundle twists as it rises. The twist tightens into a helical pattern. The helix looks like a faint corkscrew made of light. The corkscrew is not rigid. It flexes gently. It still keeps coherence. A payoff lands with that image. Twisted fields can store energy like a tightened spring. The spring is not metal. The spring is tension in the field itself. When the twist propagates outward, it can carry energy away from the center. The plasma rides with it. The plasma remains collimated by the same tension. The jet base becomes both channel and carrier. A limit of intuition arrives next. Common experience treats space as a passive stage. Here the stage moves. Paths curve even when nothing seems to push. Time itself runs differently across nearby regions. The mind expects rotation to be a property of matter. It becomes a property of space-time geometry. Another limit enters as a limit of observation. Spin is not measured by touching the horizon. It is inferred indirectly. Broad spectral shapes suggest the inner rim location. Timing patterns suggest orbital scales. Jet power suggests available energy. Each inference depends on a model of the disk and emission. Different assumptions can mimic similar signals. Resolution limits blur the inner region into a single glow. A signal would merge multiple layers into one curve. This is why spin estimates carry uncertainty. Yet the picture remains useful. Even with uncertainty, rotation organizes the environment. It sets a direction. It changes the efficiency of energy flow. Another visual anchor slows the scene again. The inner disk glows with a sharp rim. Above it, the funnel looks darker and clearer. Around the funnel, faint arcs of light curve like thin crescents. The crescents trace bent paths. The bending is stronger near the axis. The brightness gradient across the crescent suggests a changing angle. That angle changes the apparent intensity. The geometry writes its signature in gradients and asymmetry. A payoff follows from those gradients. The jet does not require a constant push like a steady wind. It can be maintained by a steady pattern of rotation and field. Rotation supplies order. Field supplies guidance and tension. Plasma supplies the material that radiates. The three components meet in a compact zone. The results extend outward to scales that dwarf the source. The scale shift returns in a soft sweep. Near the horizon, change can happen over hours. Along the jet, those changes can travel and appear as knots separated by light years. Over millions of years, the integrated effect can heat a galaxy halo. It can carve cavities in diffuse gas. It can shape large structures without any solid contact. The closing sentences settle the focus for the next step. Spin provides an axis and an energy reservoir. The next checkpoint follows the magnetic fields themselves. It traces how fields turn into rails that guide plasma into a narrow, long beam. Magnetic fields cannot be seen directly, yet they can shape a jet with quiet precision. In that region, the field behaves like a framework that guides plasma into a narrow path. The scene begins above the inner disk. A faint funnel opens like a dark corridor. Along its sides, a thin glow traces curved lines. The lines rise from the disk surface. They arch upward and inward. The arching creates a gentle X shape when seen in silhouette. Near the axis, the glow tightens into a brighter spine. The spine looks smooth at first. Then it shows subtle striations like fine layers in polished stone. A small unlock arrives early. Plasma is a gas of charged particles. Charged particles respond to magnetic fields. When the field is ordered, the motion becomes ordered. When the field is tangled, the motion spreads and heats. This is why a jet can be narrow instead of smoky. The main concepts stay few. Plasma is one, magnetic collimation is another, magnetization is the third. Magnetization means field energy dominates over particle pressure. The definition remains short and calm. Magnetization means magnetic energy outweighs the random thermal motion. The analogy stays everyday and unique. A garden trellis can guide a climbing vine into a straight column. The trellis does not push the vine forward, it limits where the vine can go. In that region, the field limits sideways drift. It also channels energy outward along a preferred route. The scale shift follows softly. The guiding structure forms near the inner rim. That rim can be smaller than a planetary orbit. Yet the guided outflow can remain coherent across distances that can exceed a galaxy's width. A tiny geometry near the center becomes a long architecture in space. Another visual anchor slows the pacing. The field lines twist as they rise. The twist forms a helix. The helix is not tight like a spring. It is wide and patient. The pitch changes with height. Near the base, the twist is denser. Farther out, it relaxes. This gradient in twist is a physical detail that matters. A stronger twist implies a stronger sideways tension. That tension can pinch the flow toward the axis. A payoff arrives with that pinch. Collimation does not require a rigid pipe. It can emerge from a balance of forces. Magnetic tension pulls inward. Plasma pressure pushes outward. The jet finds a width where these effects match. The width can stay steady over large distances. The jet then looks like a long cylinder with a bright core and a softer edge. The softer edge is a sheath. The sheath is slower and less magnetized. It acts as a buffer against mixing with the surroundings. The next checkpoint moves along the spine. Brightness varies in smooth bands. Some bands look slightly thicker. Some look slightly thinner. The edge stays defined. The center stays bright. Light behaves as if the jet has an inner lane and an outer lane. This layered appearance suggests that energy is not distributed evenly. The core carries most of it. The sheath carries less but provides stability. Another payoff arrives from that layered picture. A layered jet can survive contact with ambient gas. The outer layer absorbs shear. It can heat and radiate. The inner core stays straighter. The jet does not need to be perfectly isolated. It needs to keep its core protected. This helps explain why the beam remains narrow for so long. The main number arrives in a gentle way. The jet opening angle can be about 5 degrees, like the slight spread of a handheld fan when only a small arc is opened. This small angle matters over long distances. Even a tiny widening becomes large far away, yet the observed beam often stays remarkably thin. That thinness implies strong guiding forces near the base and sustained balance along the flow. Another scene appears where the jet meets a faint background haze. The edge of the jet shows a thin boundary layer. Brightness rises slightly along the boundary. Then it fades into the surrounding medium. The fade is gradual. It forms a soft gradient rather than a sharp cutoff. The gradient hints at mixing and heating at the interface. Waves can grow there. Small ripples can roll along the boundary. The core stays calmer. The boundary becomes the place where energy leaks outward. A limit of observation enters with calm clarity. Magnetic fields are inferred, not photographed. Their structure is reconstructed through polarization patterns and brightness changes. Those patterns depend on emission models. They also depend on how tangled fields are on small scales. If the field changes direction within a tiny region, signals can cancel. The net pattern can look weaker than the true field. Resolution limits blur many small zones into one. A signal would carry an average over tangled patches. This is why the field geometry is partly hidden. Even so, consistent polarization across a jet implies some order survives. Another limit of intuition arrives quietly. A field line is not a physical wire. It is a way to describe forces. The mind can mistake it for a solid rail. In reality, particles gyrate around the field and drift slowly across it. That drift depends on turbulence. It depends on gradients. It depends on waves in the plasma. The field guides, but it also changes with the flow. The structure is dynamic. It remains ordered enough to collimate, yet flexible enough to respond. Another visual anchor slows the final stretch. The helical pattern in the spine becomes clearer in imagination. A faint twist wraps around a bright core. The twist is visible as alternating brightness along the edges. The pattern resembles a gentle braid made of light. The braid widens slightly with distance, then it narrows again. This subtle breathing of width suggests oscillations in balance. Each oscillation can form a small knot farther out. Each knot can radiate more strongly. A payoff follows from that breathing. Variability at the base does not destroy the jet. It can become structure. The jet carries changes outward as waves and compressions. The field helps keep those changes organized. The beam becomes a record of its own guiding forces. The scale shift returns in a soft sweep. Near the base, changes unfold over hours and days. Farther out, those changes appear as bright regions separated by light years. Over millions of years, the jet can inflate enormous lobes. Yet the same basic guidance remains. A narrow spine, a buffered sheath, a tension that resists sideways spread. The closing sentences turn gently towards the next checkpoint. A guided beam still needs to move fast. The next step follows how motion changes appearance and brightness. It moves from magnetic structure to the calm effects of relativistic beaming. A jet can look brighter on one side without changing its true power. In that region, fast motion reshapes light into an uneven beam through relativistic beaming. The opening scene is a long, narrow streak that seems sharper on one side of the pair. One jet glows with a clean spine. The opposite jet looks thinner and dimmer. Both extend from the same dark center. Both keep a similar angle and straightness. The difference is brightness and contrast. The bright side shows a stronger gradient. It fades from a hot core to a soft edge over a narrow band. The dim side fades more quickly into the background haze. A small unlock arrives early. Light is not only emitted, light is also transformed by motion. When plasma moves close to light speed, emitted radiation is concentrated forward. The forward direction receives more photons, the backward direction receives fewer. This effect is not a trick of distance alone. It is a property of space-time and time dilation. The main concepts stay few. Relativistic beaming is one, Doppler shift is another, apparent speed is the third. Doppler shift means motion changes observed frequency. The definition stays short. Doppler shift means motion makes light appear bluer or redder. A calm analogy anchors the idea. A steady rain falls through still air. A fast-moving river current can sweep the falling drops into streaks. The rain stays the same. The streak pattern changes with flow. In that region, emission stays rooted in plasma processes. The pattern in the sky changes with motion toward or away from the line of sight. Another visual anchor slows the pace. Along the bright jet, faint knots appear as beads. Each bead has a soft leading edge and a sharper trailing edge. The shapes suggest compression. The beads also align along the axis like a string. Between them, the jet remains visible as a dim thread. The edge of the thread stays relatively crisp. This crispness implies the flow remains collimated. It also implies that sideways mixing is limited. A payoff arrives with those beads. Beaming can make small variations look larger. A mild compression becomes a bright knot. A gentle bend becomes a sharp change in brightness. This means the jet can seem more structured than it truly is. It also means the bright jet is not necessarily stronger. It may simply be pointed closer to the line of sight. A second payoff follows quickly. The dim counterjet is a reference. It hints at the true symmetry of the engine. If both jets carry similar power, the brightness ratio becomes a measure of speed and angle. The physical details remain concrete. The bright jet has a clear spine. The spine is surrounded by a faint sheath. The sheath is wider than the spine by a small margin. The brightness falls across the sheath in a smooth gradient. The counterjet shows a similar sheath but at lower contrast. These layers matter. Beaming is stronger for faster material. If the spine is faster than the sheath, the spine will be more boosted. The boosted spine can dominate the image. The sheath can almost vanish. A scale shift arrives with calm contrast. Near the base, the flow crosses a small region in minutes. Far from the base, the same flow can take thousands of years to traverse a visible length. Light travel time complicates the picture. Events along the jet are not seen in their local order. A signal would carry delayed information from different distances. This can make patterns seem to move faster than light. Apparent speed is a projection effect. It comes from geometry and timing. It does not require any material to outrun light. The main number arrives gently. Apparent motion can look about 10 times the speed of light, like a shadow sliding across distant hills faster than any running animal. This comparison stays quiet and safe. Shadows are patterns, not objects. In that region, bright knots are patterns in emission. Their apparent motion can exceed light speed without breaking physics. A new scene forms as the jet bends slightly. The bend is smooth and gradual. Brightness increases on the inside of the bend. It decreases on the outside. This is a clue. Angle changes alter beaming. A small turn can increase the forward boost. The inside of the bend becomes brighter. The outside becomes dimmer. A payoff arrives from this simple geometry. Changes in brightness can trace changes in direction. The jet becomes a compass needle for its own motion. Another limit of observation enters softly. Apparent speeds are inferred from repeated images separated in time. Measurements depend on identifying the same knot again. Knots can evolve as they move, they can fade and brighten, they can merge. Resolution limits can blur close knots into one. At long distances, a signal would blend several features. This makes speed estimates uncertain. Angle estimates are also uncertain. They depend on assumptions about intrinsic symmetry. They depend on models of emission. Yet even with uncertainty, beaming explains the common asymmetry. It explains why one jet is often seen more clearly. A limit of intuition follows. The mind expects brightness to measure power directly. In relativistic flows, brightness measures direction as much as energy. A faint jet can be powerful. A bright jet can be moderately powered but well aligned. This inversion is a gentle boundary of everyday thinking. It is one reason jets remain surprising. Another visual anchor arrives to keep the rhythm calm. The bright jet spine looks like a thin ribbon. It narrows slightly where the knots appear. It widens slightly between knots. The edge remains clean. The ribbon is surrounded by a dim halo of emission. The halo fades smoothly into the background. The counterjet is a ghost of the same ribbon. It is present but muted. The symmetry remains in geometry. The asymmetry remains in light. Another payoff settles in place. Beaming provides a way to connect microphysics to the large scene. It links particle motion to observed structure. It also explains why jets help reveal high speeds without touching the source. The brightness imbalance is a diagnostic. It is a tool of reasoning that uses light alone. The final scale shift widens gently. Over thousands of years, knots can travel visible distances. Over millions of years, the jet can inflate vast lobes and cavities. Yet the beaming effect remains immediate. It depends on motion at each moment. It can change quickly if the jet direction wobbles. It can also remain steady if the axis is stable. The closing sentences move toward the next checkpoint. Fast motion explains uneven brightness. The next step examines how variations in speed create shocks. It follows how knots form and how energy is dissipated along the beam. A jet can look smooth from afar, yet its light often gathers into knots like slow pulses. In that region, shocks form when faster plasma catches slower plasma and compresses it. The first scene is a narrow beam with a chain of bright beads. Each bead has a rounded front. Each bead trails a softer wake. The spine stays straight. The edges remain crisp. Between beads, the beam dims but does not vanish. The brightness rises and falls in a calm rhythm. The pattern suggests a travelling disturbance rather than a steady lamp. A small unlock arrives early. A shock is a compression wave that steepens into a sharp front. Shock means a sudden jump in density and temperature. The definition stays short and plain. Where the jump occurs, particles gain energy. Radiation increases. The knot becomes visible. The main concepts remain few. Internal shocks are one. Compression is another. Synchrotron radiation is the third. Synchrotron means light from charged particles spiraling in magnetic fields. The analogy stays everyday and unique. A long train line has cars that change speed. When a faster car approaches a slower one, spacing shrinks. The line bunches. The bunching is not a crash. It is a temporary compression that travels along the line. In that region, plasma packets act like those cars. The magnetic framework keeps the flow narrow. Variations in speed create bunching. Bunching creates shocks. A payoff settles in place. Knots are not separate objects fired like bullets. They are places where flow conditions change. A knot can brighten and fade while the underlying plasma continues downstream. This explains why knot shapes can evolve. It also explains why a jet can remain continuous even when knots appear discrete. The next visual anchor slows the pacing. One knot shows a sharp leading edge. Behind it, brightness spreads into a tapered tail. The tail blends into the jet spine. The transition is smooth. The edge of the knot is not a hard boundary. It is a thin region where compression peaks. Magnetic fields in that region can become more ordered. Their strength can increase. The enhanced field makes synchrotron radiation stronger. The knot glows more intensely. Another payoff arrives from this physical detail. Compression can amplify magnetic fields without creating new fields from nothing. Field lines are squeezed closer. Particle spirals tighten. The same number of particles can radiate more efficiently. A small change in flow can produce a large change in light. The main number arrives gently. A bright knot can span about 1 light year, like a ribbon of fog stretching between two distant hills. This scale is enormous compared with the launch region. It is still small compared with the full jet length. The scale shift is calm and clear. The base sets conditions within hours or days. Farther out, those conditions appear as structures a light year across. The journey from small to large is carried by motion near light speed. Another scene forms along the boundary of the jet. The sheath looks dimmer. It shows faint ripples. The ripples move slower than the knots in the spine. This layered motion matters. The spine can host internal shocks. The sheath can damp them. The interface between spine and sheath can also create shear. Shear can stir turbulence. Turbulence can broaden the jet slightly. Yet the core remains narrow. The physical detail is a gradient. Speed is highest on the axis. It decreases toward the edge. This gradient helps keep the jet coherent. It also shapes where shocks are strongest. A payoff follows from the gradient. If faster flow is concentrated in the spine knots, will appear most strongly on the spine. The sheath will glow more gently. This is often what images suggest. The brightest emission traces the fastest lane. The dimmer emission traces the protective layer. The jet becomes a layered river of energy. Another visual anchor arrives with a gentle bend. As the jet curves, a knot brightens on the inside of the curve. The outside dims. This hints at beaming changes. It also hints at compression changes. The inside of a curve can squeeze flow lines closer. That squeeze can intensify shocks. The knot becomes a marker of both geometry and dynamics. Another payoff arrives. Knots can be used to infer how steady the engine is. Regular spacing suggests a repeating variation near the base. Irregular spacing suggests chaotic feeding. Even when the base cannot be resolved, the knot chain records its behavior. The record is not perfect. It is filtered by travel time and cooling. It still carries clues. A limit of observation enters softly. Knots are identified by the brightness peaks. Peaks can merge if resolution is limited. They can split if the emission shifts. Cooling changes can alter the shape. A signal would blend several compressed regions into one luminous patch. This makes shock counts uncertain. It also makes spacing uncertain. Models must assume a flow speed and viewing angle to translate spacing into time. Small errors in those assumptions propagate. Yet the shock picture remains robust. Where speeds vary, compression forms. Where compression forms, synchrotron brightens. Another limit of intuition follows. A shock is often imagined as a violent collision. In a relativistic jet, it is a moving pattern in a plasma flow. The particles and fields pass through the front. The front itself can persist. It can drift and change. It can fade as energy is lost. This is why a knot can appear brighten and dissolve without any solid boundary. The mind expects a fixed object. The reality is a traveling transition. Another visual anchor slows the closing stretch. A knot fades into a smooth spine. The spine continues as a thin thread. Farther ahead, another knot forms. The chain looks like a quiet heartbeat along a single line. The edges remain clean. The background remains faint. The rhythm remains steady. A payoff lands gently. Shocks are not only decoration. They are where energy is converted into radiation. They are also where particles are accelerated. This means the visible jet is often a map of its own dissipation. It shows where the flow pays a cost to remain organized. The scale shift widens one more time. A knot can brighten over years. A lobe can inflate over millions of years. Both depend on the same flow carrying energy outward. The next checkpoint follows what happens after many shocks. It traces how the jet interacts with surrounding gas and how boundaries mix and heat. A jet carries energy outward, yet its edges are always in contact with something colder and slower. In that region, shear and mixing at the boundary decide whether the beam stays narrow or frays. The first scene is a long column moving through a faint haze. The column has a bright core. It has a dim sheath. Between sheath and haze, a thin boundary layer forms a soft rim. The rim is not a hard line. It is a gradient where brightness and speed change together. The jet edge shows faint ripples. The ripples drift downstream. They look like gentle folds along fabric carried by a steady current. A small unlock arrives early. Shear means neighboring layers move at different speeds. Shear can feed instabilities that wrinkle the boundary. The wrinkles can pull ambient material inward. They can also push jet material outward. This is how mixing begins. The main concepts stay few. Shear is one. Entrainment is another. Entrainment means the jet drags surrounding gas into the flow. The third concept is stability. Stability means small ripples do not grow without limit. A calm analogy anchors the idea. A clear stream flows through still pond water. The stream stays distinct for a while. Its edges begin to curl. Small swirls peel off and roll back. The stream does not vanish at once. It gradually shares its momentum with the pond. In that region, a relativistic jet is the stream. The surrounding medium is the pond. The difference is extreme speed and strong magnetic guidance. A payoff settles in place. The sheath matters because it is a buffer. If the core meets the ambient gas, directly mixing grows quickly. If the sheath absorbs the shear, the core can remain intact. The jet can then stay narrow for a long distance. The boundary becomes the sacrificial layer. It can heat and radiate. It can thicken. It can slow. The spine stays fast. The next visual anchor slows the pace. The jet edge shows alternating bright and dim bands. The bands follow the outline of the column. They are slightly tilted. The tilt suggests a wave wrapping around the jet. The wave does not tear the jet apart. It rolls along like a slow spiral crease. This crease is a physical detail. It implies a helical distortion at the boundary. Another payoff arrives from that detail. A helical distortion can be a sign of a growing instability. It can also be a sign of a jet that remains coherent while it flexes. Flexing is not failure. It can be part of how the jet survives. A flexible boundary can radiate energy and reduce stress on the core. The main number arrives gently. The boundary layer thickness can be about 10 light years, like a thin fog bank hugging the edge of a long valley wall. This thickness is small compared with the jet length. It is large compared with the launch region. The scale shift is calm and clear. Near the black hole relevant scales can be smaller than a solar system. Far out the boundary is measured in light years. The same flow carries structure across this span. Another scene form is where the jet passes through a denser pocket of gas. The column narrows slightly. The sheath brightens. The edge gradient steepens. A faint bow-like brightening appears ahead of the sheath. The brightening is subtle. It suggests compression of ambient gas. The jet does not stop, it adjusts. The boundary absorbs the interaction. A payoff follows. The jet can carve a channel by pushing ambient gas aside. Once the channel exists, later flow can travel more smoothly. The first passage is costly, the next passage is easier. This is one way a jet maintains a long path. It gradually builds its own corridor through the medium. A limit of observation enters softly. The boundary layer is faint. Its emission can be below detection thresholds. It can be confused with background haze. Resolution limits can smear the edge into the core. A signal would mix sheath light with ambient light. This makes the true thickness uncertain. Models must assume particle distributions and field geometry to interpret brightness. Different assumptions can produce similar edge gradients. Even so, the presence of edge, ripples and widening gives strong hints that mixing occurs. Another limit of intuition follows. Mixing is often imagined as the instant blending. In turbulent flows, mixing can be patchy and layered. Pockets of ambient gas can be carried inside without fully dispersing. Pockets of jet plasma can leak outward without dissolving at once. The boundary can be a mosaic of filaments and vortices. This makes the jet look fuzzy at the edges, while the core stays sharp. Another visual anchor slows the closing stretch. A faint filament peels off from the sheath. It drifts outward like a thread of smoke in still air. The filament curls and fades. The core remains straight. The sheath remains present but thickens slightly after the peel. This image carries a payoff. Entrainment does not need to destroy the jet. It can be a controlled loss. The jet can shed energy and a mass at the edges while preserving its central channel. This controlled loss can also explain why jets inflate broad lobes far away. The material that leaves the boundary can feed the cocoon around the jet. The scale shift widens gently again. Over hundreds of thousands of years, repeated interactions can widen the sheath. Over millions of years, the cocoon can grow into a lobe that dwarfs the host galaxy. The small ripples along the edge can contribute to that vast structure. The closing sentences turn softly toward the next checkpoint. Boundary mixing decides how the jet survives on its journey. The next step follows the journey to its endpoint, where the beam meets resistance and forms a bright termination region. A jet can travel for vast distances, yet it must eventually slow and hand its energy to the surrounding space. In that region, a termination shock forms where the beam meets enough resistance to stop behaving like a narrow spear. The first scene is far from the galaxy center. The jet remains a thin line across a dark background. Then it brightens suddenly at a compact spot. The spot is not large. It is a concentrated glow at the jet's end. Behind it, a broad, faint cloud spreads outward. The cloud has a rounded edge. It looks like a soft bubble, with a dim interior and a brighter rim. The compact spot sits on the bubble's inner edge, like an ember pressed against glass. A small unlock arrives early. The jet does not fade away smoothly, it often ends at a shock front. The front converts bulk motion into heat and turbulence. This conversion feeds a wide region called a lobe. The main concepts remain few. Termination shock is one, cocoon pressure is another. Cocoon means the hot surrounding region inflated by the jet. The third concept is backflow. Backflow means shocked material flows back along the jet's sides. The definition stays short and plain. Backflow means heated plasma returns toward the center inside the cocoon. The analogy stays everyday and unique. A garden hose aimed at a sandbank forms a bright splash point. Water slows there, then it spreads sideways and backward in shallow sheets. The hose stream stays narrow before impact. The splash region becomes broad after. In that region, the jet is the hose stream. The hotspot is the splash point. The lobe is the spreading sheet, but on a scale that can fill into galactic space. A payoff settles in place. A hotspot marks where the jet deposits energy most abruptly. It is not only a bright marker, it is a boundary in the flow. Upstream, the jet is fast and collimated. Downstream, the motion becomes chaotic and subsonic relative to the local plasma conditions. The physical details remain clear. The hotspot has a sharp leading edge. Its brightness peaks at a small area. The edge is often crescent-shaped. The brightness falls into a trailing plume. That plume feeds the lobe. The lobe shows a soft brightness gradient. It brightens near the edges. It dims toward the center. The edge can appear as a curved rim where compressed plasma accumulates. Another visual anchor slows the pacing. Inside the lobe, faint filaments thread the glow. Some filaments curve back toward the jet axis. Others spread laterally. These threads suggest backflow and mixing. The cocoon surrounds the jet like a warm envelope. The envelope exerts pressure inward. That pressure can help keep the jet narrow upstream. It can also steer the jet slightly if the environment is uneven. A payoff arrives from this envelope. The jet is not isolated from the lobe it creates. The lobe acts as a memory of past activity. It holds energy for long periods. It also sets boundary conditions for the jet's later path. If the cocoon is overpressured, it can pinch the beam. If it expands, it can create a low-density channel. The next outflow then travels more freely. The main number arrives gently. A lobe can grow to about 100,000 light-years across like a fog bank spanning an entire chain of distant mountains. This scale is enormous compared with the launch region near the black hole. The scale shift is calm and steady. Near the base, structures can be smaller than a planetary orbit. At the end, the system sculpts volumes that can rival the size of a galaxy. The same flow connects both ends. Another scene forms at the lobe boundary. The outer rim is slightly brighter. It is smoother than the filaments inside. The rim suggests a contact discontinuity. Contact discontinuity means a boundary separating fluids without mixing fully. The definition stays short. Contact discontinuity means two plasmas touch while remaining largely separate. The boundary is not perfectly stable. It can ripple. It can grow fingers. It can also remain smooth for long intervals. A payoff arrives from this boundary idea. The lobe can store energy without instantly giving it away. Its boundary limits mixing with the external medium. This slows cooling. It allows the lobe to remain visible and influential. The lobe can push on the surrounding gas. It can carve cavities. It can lift and stir the medium over huge scales. The jet thus becomes a feedback mechanism that connects a compact engine to a vast environment. A limit of observation enters softly. The termination region is far away and faint. Different wavelengths trace different particle energies. Emission depends on magnetic fields and particle distributions. These are inferred, not directly measured. Resolution limits can blur the hotspot into a larger patch. A signal would blend the shock front with nearby backflow. This makes it hard to map the exact shock geometry. Models must assume the jet speed and density. They must also assume how efficiently particles are accelerated. Different assumptions can reproduce similar brightness profiles. Yet the existence of a compact hotspot and a broad lobe is a strong clue that a termination shock is present. Another limit of intuition follows. The mind expects the jet to behave like a rigid lance that pierces forever. In plasma, resistance accumulates. Even a narrow beam must do work on its surroundings. Eventually the work slows it. The endpoint is not a sudden stop like a wall. It is a region where momentum is redistributed. The jet's kinetic energy becomes heat turbulence and radiation. The system shifts from directed flow to stored pressure. Another visual anchor slows the closing stretch. The hotspot glows like a small bright seed. Around it, the lobe looks like a quiet lantern shade. The inner filaments drift in arcs. The outer rim forms a smooth curve and the jet enters the hotspot as a thin line. It loses its identity there. Its energy spreads into the cocoon. A payoff lands gently. The termination shock is the place where a long journey pays its final cost. It also clarifies the meaning of collimation. Collimation is not only about staying narrow. It is about delivering energy to a specific location far away. The beam becomes a delivery channel. The hotspot becomes the delivery point. The lobe becomes the reservoir. The scale shift widens one more time. A hotspot can flicker over years. A lobe can persist over millions of years. The jet's endpoint can migrate as the environment changes. It can also shut off and leave a fading bubble. The closing sentences turn softly toward what follows. A lobe does not remain static. It rises, expands, and interacts with larger gas structures. The next checkpoint widens to the environment and shows how jets carve cavities and reshape diffuse media. A jet leaves behind more than light. It leaves a hollow in hot gas that can persist long after the beam fades. In that region, a lobe inflates a cavity and changes how surrounding plasma cools and flows. The first scene is a vast, faint atmosphere around a galaxy group. The atmosphere glows softly in diffuse light. Inside it, two dim voids appear like missing patches. Each void has a rounded outline. Each void is bordered by a thin, bright rim. The rim is a compressed shell where gas density rises. The interior looks darker because it is lower density. The pair of cavities sits on opposite sides of the central galaxy. Their symmetry suggests a common origin. A small unlock arrives early. A cavity is a volume where jet-inflated plasma displaces the ambient medium. The ambient medium remains present around it. It presses inward. The cavity pushes outward. The balance creates a stable bubble for long spans. The main concepts stay few. Cavity inflation is one, buoyancy is another. Buoyancy means lighter plasma rises through heavier plasma. The third concept is feedback. Feedback means energy input offsets cooling. The analogy stays everyday and unique. A warm air pocket rises through a cooler lake of fog. The pocket does not remain in place. It drifts upward. It leaves a trail of disturbed fog. In that region, the cavity is the warm pocket. The surrounding hot gas is the foggy lake. The cavity rises slowly because the surrounding medium supports it. A payoff settles in place. Cavities are not only passive scars, they are channels by which jet energy is stored and redistributed. Instead of radiating away immediately, energy becomes pressure and motion in the hot gas. This can delay cooling. It can also stir the medium and spread heat. The next visual anchor slows the pacing. The cavity rim looks like a thin crescent. It is brighter at the leading edge. Behind it, faint filaments curve. These filaments suggest uplifted gas. The cavity drags material as it rises. The dragged material forms a wake. The wake is not a straight line. It curls gently. The curl hints at turbulence. Another payoff arrives from the rim and wake. The rim marks where work is done on the medium. The wake marks where the medium responds. Together, they show that a jet can influence volumes far larger than the beam itself. A narrow flow becomes a broad restructuring. The physical details remain concrete. The cavity boundary is a contact discontinuity. It separates the low plasma from the ambient plasma. The boundary can be stable for a time. It can also ripple. Small ripples can grow into scalloped edges. The rim can thicken where instabilities mix layers. The cavity interior can hold faint radio-emitting plasma while being dark in other bands. The contrast is a clue to composition and density. The main number arrives gently. A typical cavity can be about 50,000 light-years across, like a calm bay carved out of a coastline that spans many mountain valleys. This scale is enormous compared with the jet base. The scale shift is calm and clear. Near the black hole, changes unfold over hours and days. Here the imprint is measured in tens of thousands of light-years and persists for millions of years. The same engine produces both. Another scene forms as the cavity rises. The pair of voids is not perfectly aligned. One sits slightly higher. Its rim is broader. Its wake is longer. This suggests different ages. The higher cavity has had more time to drift. Buoyancy moves it outward. As it rises, pressure drops. The cavity expands. The rim can weaken. The boundary can become more ragged. A payoff follows from this slow drift. The medium does not need continuous jet input to remain disturbed. A single episode can create a bubble that travels. That travel transports energy away from the center. It also transports magnetic fields and particles. The cavity becomes a slow conveyor for the environment. A limit of observation enters softly. Cavities are inferred from brightness deficits in diffuse emission. That emission depends on density squared. Small changes in density can produce large brightness changes. Projection effects can hide or mimic cavities. A void along the line of sight can be partially filled by foreground and background emission. Resolution limits can smooth edges. A signal would blend rim and interior. This makes cavity size and depth uncertain. Models must assume the three-dimensional shape. They must also assume the ambient density profile. Yet the rim compression and paired symmetry strongly support a jet origin. Another limit of intuition follows. The mind expects heat to spread like a uniform bath. In a stratified plasma, heat distribution is complex. Buoyant bubbles rise and do work. They excite waves and turbulence. Some energy becomes gentle sound like ripples. Some becomes mixing at boundaries. Some becomes lifted low-entropy gas that later falls back. The path from jet power to thermal balance is indirect. It is also variable. This is why feedback can stabilize without fine-tuning in every moment. Another visual anchor slows the closing stretch. Around the cavity rim, faint concentric ripples appear in the surrounding glow. Each ripple is a subtle bright arc. The arcs are spaced smoothly. They suggest pressure waves traveling outward. The waves are not violent. They are gentle compressions that carry energy through the medium. A payoff lands with these arcs. Jets can heat their surroundings without strong shocks everywhere. Repeated gentle waves can distribute energy over large volumes. This reduces cooling in the core. It can also prevent dense gas from condensing quickly. The cavity and ripples together show a calm mechanism of influence. A narrow beam creates a broad thermostat. The scale shift widens one more time. Over a few million years, a cavity can rise and fade. Over tens of millions of years, multiple cavities can stack into a pattern. The environment becomes layered with old bubbles. The present jet episode becomes one chapter in a longer cycle. The closing sentences turn softly toward the next checkpoint. Cavities show how jets reshape hot gas. The next step follows how this reshaping changes the host galaxy and its larger halo over deep time. A jet can act like a quiet regulator, shaping how a galaxy's gas stays hot or cools into denser phases. In that region, feedback links a compact engine to the thermal balance of an enormous halo. The first scene is a galaxy surrounded by a faint extended glow. The glow is not uniform. It brightens towards the center. It fades outward in a smooth gradient. Embedded inside are dim cavities with thin bright rims. Between the rims, filamentary gas hangs like soft drapery. The filaments curve gently and appear cooler and denser than their surroundings. They do not fill the whole halo. They trace narrow paths as if lifted and then left suspended. A small unlock arrives early. Feedback means energy output changes the conditions that feed the output. In this setting, jet energy heats and stirs halo gas. Heated gas cools more slowly. Slower cooling reduces the inward supply that powers the central activity. The cycle can stabilize without perfect timing. The main concepts stay few. Cooling time is 1. Cooling time means how long hot gas takes to lose heat by radiation. The second concept is uplift. Uplift means cavities lift denser gas to higher altitudes. The third concept is precipitation. Precipitation means cold gas condenses out of hot gas in patches. The definition stays short and calm. Cooling time means the time required for plasma to radiate away its heat. The analogy stays everyday and unique. A simmering pot can be kept from boiling over by gentle stirring. The heat source stays on, the motion redistributes heat. Steam and bubbles change. The pot settles into a steady simmer instead of a runaway boil. In that region, the halo is the pot. The jet-inflated cavities are the stirring. The radiative cooling is the tendency to lose heat and condense. A payoff settles in place. Jets do not need to blast the halo into uniform heat. They can prevent a central runaway by distributing energy where cooling would be fastest. Cavities and ripples act as carriers. The halo receives energy in intermittent broad patterns. The next visual anchor slows the pacing. A cavity rises away from the center. Its rim remains faintly bright. Behind it, a trailing filament stretches like a ribbon. The ribbon is denser and cooler. It does not fall straight. It arches and curls in a gentle loop. The cavity leaves a wake that looks like a soft swirl. Another payoff arrives from this loop. Uplift can move low-entropy gas outward. Low-entropy gas is gas that is dense and cool relative to the ambient halo. When lifted to lower pressure regions, it can expand. Expansion can cool it further. This can promote condensation into cold filaments. The jet thus can both heat and encourage localized cooling. The outcome depends on balance and timing. The physical details remain concrete. The cavity rim is a compressed shell. The shell has a sharper brightness gradient than the surrounding halo. The filament is narrow. It has a braided appearance. It shows small clumps along its length. The clumps suggest local condensation. The halo background remains smooth but not featureless. Faint arcs suggest weak pressure waves traveling outward. A payoff follows from the clumps. Cooling and condensation are not uniform. They happen where density is slightly higher or where uplift changes conditions. This means feedback can be patchy and still effective. The halo can remain mostly hot while allowing some cold material to form in filaments. That cold material can later drift inward. The cycle continues. The main number arrives gently. A typical cooling time in the core can be about 1 billion years, like the slow aging of a mountain range under steady weather. This timescale is vast compared with the rapid variability near the black hole. The scale shift is calm and clear. Near the central engine, changes can occur over hours to days. In the halo, the response unfolds over hundreds of millions to billions of years. The jet is a bridge between these domains. Short episodes can accumulate into long-term regulation. Another scene forms as multiple cavities appear at different radii. Some are close in, their rims are sharp, some are far out, their rims are diffuse. The pattern suggests repeated activity. Each cavity is a chapter. The halo becomes layered with old bubbles. Their shapes can be slightly tilted. This implies the jet axis can precess or drift. The drift spreads energy over a wider volume. A payoff arrives from this layering. Repetition can prevent the halo from settling into a single dense core. Each bubble displaces gas and excites motion. Motion becomes turbulence. Turbulence becomes mixing and gentle heating. The halo remains supported by pressure and motion rather than collapsing. A limit of observation enters softly. Feedback cycles are inferred from snapshots. Time is not directly watched across 1 billion years. Cavity ages are estimated from sizes and buoyant rise speeds. Those estimates depend on ambient density profiles. They depend on cavity shapes that are not perfectly known in 3 dimensions. Projection effects can hide cavity depth. A signal would blend front and back layers of the halo into one image. This makes precise energy budgets uncertain. Models must fill in missing geometry and particle content. Yet the repeated pattern of cavities and rims strongly supports ongoing energy injection. Another limit of intuition follows. It is tempting to imagine a thermostat that holds one exact temperature. Real halos are stratified. They have gradients. They have local fluctuations. Heating does not perfectly match cooling everywhere. Instead, the system hovers near a threshold. When cooling becomes too strong, more condensation can occur. That can increase central fueling and drive stronger outflows. When heating dominates, condensation decreases. Fueling slows. The cycle self-adjusts. This is regulation without precision control. Another visual anchor slows the closing stretch. A faint ripple expands across the halo glow as a broad arc. The arc is subtle. It is a gentle compression. It spreads outward like a slow ring in a pond. The ring fades as it moves. Behind it, the halo remains smooth. Another payoff lands with this ring. Even weak waves can carry significant energy over large volumes. They can gently raise entropy and delay cooling. Combined with turbulence and mixing, they help maintain the halo's long-term structure. The jet's influence becomes quiet but persistent. The scale shift widens one more time. Cavity can rise over tens of millions of years. A sequence of cavities can shape a halo over billions of years. Meanwhile, the central engine can vary on timescales shorter than a season. The system connects these extremes through energy transport and delayed response. The closing sentences turn softly toward the next checkpoint. Feedback shapes the halo and the host galaxy over deep time. The next step widens further to show how jets influence larger environments beyond a single halo, including group and cluster scales. A jet can reshape not only one halo, but a whole region where many galaxies share the same hot atmosphere. In that region, repeated outflows spread energy through group and cluster gas and change its large-scale texture. The first scene is a wide field of faint glow, smooth at first glance. Then subtle structures emerge. Long arcs curve across the glow like gentle brushstrokes. Between arcs, dim cavities appear as rounded voids. Some cavities are paired, some are offset. Their rims are slightly brighter than the background. The rims trace compressed shells. Inside the shells, emission is reduced. A small unlock arrives early. Cluster gas is a vast plasma reservoir. Jets inject energy into this reservoir through bubbles, waves, and mixing. The injection does not need to be uniform to matter. It needs to be persistent enough to prevent runaway cooling in the densest regions. The main concepts stay few. Intracluster medium is 1. Intracluster medium means the hot plasma filling a cluster. The second concept is entropy. Entropy means heat content relative to density. The third concept is stirring. Stirring means motions that mix layers and spread energy. The analogy stays everyday and unique. A slow spoon swirl in thick soup can move heat from the bottom to the surface. The soup does not become perfectly uniform. It becomes less prone to burning in one spot. In that region, jets are the slow spoon swirl. The cluster plasma is the soup. Cavities and ripples are the visible traces of stirring. A payoff settles in place. Large-scale structure can be controlled by small-scale engines because energy travels through intermediaries. Bubbles rise, waves propagate, turbulence mixes. Each step spreads influence farther than the jet itself. The next visual anchor slows the pacing. A large cavity sits tens of thousands of light years from the center. Its rim is smooth, its interior is dim. Behind it, a faint trail curves back inward. The trail looks like a soft ribbon of uplifted gas. Nearby, a second cavity appears at a different angle. Its rim is fainter. This suggests a previous episode. The pattern resembles overlapping footprints in sand. Each footprint is a bubble. The surface records a history of steps. A payoff arrives from this overlap. Multiple jet episodes can distribute energy across many directions. This prevents heating from being focused along one narrow axis. The cluster core then receives energy in a wider volume. This can raise entropy and slow cooling. The physical details remain clear. Rims are brighter because density rises at the compressed boundary. Brightness falls toward cavity centers because density is lower. Edges can be scalloped where instabilities roughen the boundary. Filaments can hang where uplift pulls denser gas outward. The background glow can show faint arcs that indicate pressure waves. Another visual anchor appears as a broad arc ripples outward. The arc is gentle. It is a slight enhancement in brightness. It curves like a quiet ring. The ring expands through the plasma. Its curvature follows the cluster's gravitational shape. The ring fades gradually as it travels. Another payoff arrives with the ring. Even weak waves can carry substantial energy when the medium is enormous. The wave energy is distributed across a large area. It can be dissipated slowly. This provides gentle heating without strong shocks everywhere. The cluster becomes a resonant cavity for pressure fluctuations. The main number arrives gently. The cluster hot atmosphere can extend about 10 million light years across like a fog sea, spanning the distance between far separated mountain ranges. This scale dwarfs any single galaxy. The scale shift is calm and steady. A jet originates near a black hole on scales smaller than a solar system. Its influence can reach volumes millions of light years wide. The path is not direct. It's mediated by bubbles, waves, and mixing that operate on intermediate scales. Another scene forms at the edge of a cavity rising through the plasma. The cavity expands slightly as pressure drops. Its rim thins. Behind it a wake forms. The wake is a region of disturbed gas with a smoother gradient. It is slightly warmer and less dense. It drifts and mixes into the background. This is how energy spreads beyond the cavity itself. A payoff follows from the wake. Heating does not require uniform temperature increase. It can occur as redistribution. Dense gas is lifted. Low entropy material is moved outward. High entropy material can flow inward. The net effect can stabilize the core without erasing structure. Entropy is a useful measure because it tracks how easy it is for gas to cool and condense. Raising entropy near the center makes condensation less likely. Another limit of observation enters softly. Cluster structures are inferred from surface brightness maps. Surface brightness is a projection. Front and back layers overlap. Cavities can be hidden if aligned along the line of sight. Ripples can be washed out by noise. Resolution limits can smear small cavities into a smooth core. A signal would merge multiple bubbles into one broad depression. This makes it difficult to count episodes precisely. Energy estimates depend on cavity volumes and ambient pressures that vary with radius. Models must assume shapes and ages, yet the repeated appearance of rims and voids across many systems supports the same underlying physics. Another limit of intuition follows. It is tempting to think of clusters as static spheres. They are dynamic. Gas sloshes due to mergers and motions. These background flows can interact with jet bubbles. They can tilt them. They can stretch them into arcs. They can break them into smaller bubbles. The jet imprint is thus shaped by a moving environment. This makes each system look different even when the same processes operate. Another visual anchor slows the closing stretch. A pair of cavities rises like two dark balloons. Their rims remain faintly bright. Between them, the central glow is smoother. Farther out, older cavities appear as barely visible dimples. The cluster looks layered with relics of activity. The relics are not dramatic. They are subtle changes in brightness and curvature. A payoff lands gently. These relics show that jets act repeatedly. They maintain a long-term dialogue between a central engine and a cluster atmosphere. The outcome is a regulated core where cooling and heating remain in tension. The scale shift widens one more time. A single bubble can rise for tens of millions of years. A sequence of bubbles can shape a cluster core over billions of years. The same fundamental mechanisms repeat: displacement, compression, wave propagation, mixing. The closing sentences turn softly towards the next checkpoint. Large environments preserve a long memory of jet activity. The next step returns to the jet itself and examines how its axis can drift and precess, spreading influence in time. A jet can point in one direction for a long time, yet subtle changes in its aim can redraw the entire pattern it leaves behind. In that region, precession and axis drift spread energy across space by slowly moving the jet's path. The first scene is a wide lobe filled with faint glow. Inside it, the bright jet does not form a single straight line. It traces a gentle curve. Farther out, the curve becomes an S shape. The S shape is broad and smooth. It is not a sharp kink. Along the curve, brightness varies in soft knots. Around the curve, older plasma forms a dim cocoon. The cocoon looks like layered smoke in still air with overlapping arcs that suggest different epochs. A small unlock arrives early. The jet is not always fixed to one axis. The axis can drift or precess. Precession means the axis slowly sweeps a cone. The definition stays short and calm. Precession means the jet direction rotates slowly around a tilted axis. The main concepts stay few. Precession is one. Alignment torque is another. Alignment torque means forces that try to align spin and flow. The third concept is duty cycle. Duty cycle means the fraction of time the jet is active. The analogy stays everyday and unique. A sprinkler head rotates and sends a stream across a lawn. The water stream remains narrow. The wet pattern becomes broad because the aim shifts. In that region, the jet is the narrow stream. The lobe and cocoon are the wet pattern. The axis drift is the slow rotation. A payoff settles in place. A curved jet does not require the plasma to turn sharply in one instant. It can reflect a slow change in the launch direction over long time. The flow emitted earlier travels outward, along the earlier direction. Later flow follows a slightly different track. The sky then shows a curve. The curve is a time record written in space. The physical details remain clear. The jet has a brighter inner spine and a dim outer sheath. The spine follows the curve more sharply. The sheath blends into the cocoon. The brightness gradient across the jet remains present. It is brighter on the inside edge of the curve. It is dimmer on the outside edge. This suggests beaming and compression effects. The curve can modestly change the viewing angle. It can also compress flow on the inside of a bend. Another visual anchor slows the pacing. Far from the center, a pair of older lobes appears at a slightly different angle. They are faint. Their rims are diffuse. The newer jet points between them. The scene resembles layered brush strokes on a dark canvas. Each brushstroke is a past direction. Each is broader and softer with age. A payoff arrives from this layered geometry. Axis changes can prevent energy from being deposited into the same channel repeatedly. This reduces the chance that the jet simply drills a single tunnel and escapes. By painting different directions, the jet heats and stirs a wider volume. Feedback becomes more effective because the target region grows. The main number arrives gently. A precession period can be about 100,000 years, like the slow cycle of glaciers shaping a valley wall. This timescale is long compared with the formation of individual knots. It is shorter than the lifetime of a large lobe. The scale shift is calm and steady. A knot can brighten over years. A curved jet track can reflect tens of thousands of years. A full lobe structure can persist for millions of years. The same system carries all three timescales at once. Another scene forms near the jet base in unresolved light. The inner beam appears straight at small scales. Then the direction changes gradually with distance. This is a clue. The launch direction can remain stable over short times. The long-term direction can wander. This can happen if the accretion flow orientation changes. It can also happen if the black hole's spin axis slowly aligns with inflowing material. Alignment torque can damp recession over time. It can also produce slow drift rather than a clean rotation. A payoff follows from this. The jet shape is a probe of hidden geometry near the engine. Even when the base cannot be resolved, the large-scale curve implies a changing launch axis. The cocoon becomes an archive of that change. Duty cycle adds another layer. If the jet turns on and off, the curve can appear as separated segments. Gaps can form. Older segments fade. New segments brighten. The lobe then shows nested structures. It can look like a series of shells or arcs. This nested pattern is a physical detail. It suggests repeated inflation episodes. It also suggests that axis drift continues across episodes. Another payoff arrives. By combining duty cycle and precession, a single engine can create complex morphologies. The complexity does not require multiple engines. It can arise from time. It can arise from slow changes in orientation and activity. A limit of observation enters softly. Curves can be caused by environmental winds and density gradients. They can also be caused by projection effects. A true three-dimensional helix can appear as a simple S shape in projection. Resolution limits can hide small bends and exaggerate large ones. A signal would blend overlapping segments along the line of sight. This makes it hard to reconstruct the true precession cone and period. Models must assume jet speed and inclination. They must also assume how quickly the cocoon fades. Different combinations can fit the same image. Yet some signatures are robust. Smooth symmetric S-shapes often suggest precession, rather than random deflection. Nested lobes often suggest episodic activity. Another limit of intuition follows. The mind expects direction changes to be abrupt. In these systems, changes can be slow and continuous. The jet is not a rigid rod. It is a guided flow whose guide can tilt. A small tilt today becomes a large separation far away because distance magnifies angle. This is a gentle geometric truth. Small angles make large offsets at large radii. Another visual anchor slows the closing stretch. The curved jet fades into the cocoon. The cocoon shows two faint arcs that do not match the current jet. The arcs are like old rings of smoke that have drifted and spread. Their edges are soft. Their centers are dim. The present jet draws a fresh line across them. A payoff lands gently. Precession and drift help distribute energy. They also help explain why jet systems can fill broad lobes rather than narrow tunnels. The jet is a moving pencil. The lobe is the shaded region built over time. The scale shift widens one more time. Over 100,000 years, direction can sweep a noticeable arc. Over millions of years, many arcs can overlap and inflate a large cocoon. The closing sentences turn softly toward the next checkpoint. Changing aim shapes large environments and preserves a memory of motion. The next step follows how jets age and fade and how relic structures remain as quiet evidence long after emission weakens. A jet does not vanish when its brightness fades. In that region, the beam leaves relic lobes that dim into near silence while still shaping their surroundings. The first scene is a wide, faint glow with an edge that is hard to see. The edge is not sharp, it is a soft gradient that blends into darkness. Inside the glow, the center looks emptier than expected. The brightest spine is gone. Only a broad haze remains. The haze is uneven. It contains pale arcs and thin filaments that curve like slow currents. A small unlock arrives early. Jets can switch off or weaken while their lobes remain inflated. The lobes then become archives of past activity rather than active channels. The main concepts stay few. Synchrotron aging is one. Synchrotron aging means radiating particles lose energy over time. Adiabatic expansion is another. Adiabatic expansion means a bubble cools as it expands without heat input. The third concept is a relic spectrum. A relic spectrum means emission shifts toward lower frequencies as particles age. The definition stays short and calm. Synchrotron aging means fast electrons lose energy while spiraling in magnetic fields. The next 2 sentences return to plain imagery. In that region, the lobe is a reservoir of charged particles and fields. The reservoir leaks its brightness slowly. The why is simple and important. The fading reveals how long energy persists after the engine quiets. A new analogy appears and stays unique. A fog bank at dawn thins as the air warms and mixes. The fog does not stop existing at a line. It becomes more transparent. Shapes inside become harder to trace. In that region, the lobe is the fog bank. The ambient plasma is the wider air that mixes around it. A payoff lands gently. A relic lobe can still store pressure even when it becomes faint. The lobe can still displace surrounding gas. It can still buoyantly rise and drift. The next visual anchor slows the pacing. Along one side of the relic, a curved rim is barely brighter than the background. The rim forms a long arc. The arc suggests a boundary where density and magnetic field are slightly higher. Inside the arc, brightness falls inward in a smooth gradient. Near the center, the glow is mottled. Small patches appear like islands of faint light. Another payoff arrives. The brightest regions fade first at high frequency. The remaining glow becomes dominated by lower energy particles. This shifts the lobe's appearance across the spectrum. The physical details remain concrete. Filaments inside the relic can look thicker than in an active lobe. The filaments can appear braided. Their edges can blur as turbulence mixes layers. The outer boundary can become ragged. Small scallops can form where instabilities disturb the contact surface. A gentle scale shift enters. Near the jet base, conditions can change quickly. In the relic, changes unfold over immense spans. The same system spans both without strain. The main number arrives softly. The bright phase of a lobe can fade over about 10 million years, like the time required for a coastline to smooth under steady waves. This timescale is long compared with any rapid flicker near the engine. It is short compared with the age of a galaxy group. Another visual anchor appears within this span. A relic bubble rises through a diffuse atmosphere. The bubble expands as pressure drops. Its interior becomes even fainter. Its rim weakens. Behind it, a wake trails as a slightly brighter ribbon. The ribbon curves. It suggests uplifted gas that later settles. A payoff follows from this rise. Adiabatic expansion reduces particle energy without direct radiation. The lobe cools by doing work on its surroundings. This can dim the lobe even if particles remain present. The lobe becomes a larger volume with lower brightness. The boundary remains as the main clue. Another payoff arrives soon after. Synchrotron aging leaves a signature in how brightness changes with frequency. Older regions appear steeper in spectrum. Steeper means brightness drops faster at higher frequencies. This gives a clock of sorts. It is not perfect, it is still useful. A limit of observation enters softly. Relic lobes can sit near the noise floor of measurements. Sensitivity limits can erase the faintest edges. Resolution limits can smear thin rims into the background. Projection can hide a bubble if it lies along the line of sight. A signal would blend foreground and background glow. This makes volume estimates uncertain. Magnetic field strength is inferred indirectly. Particle distributions are inferred indirectly. Age estimates depend on these assumptions. Different assumptions can shift the inferred time by large factors. Yet the overall story remains robust. Lobes fade by radiation and expansion. Another limit of intuition follows. The mind expects energy to be visible if it exists. In plasma, energy can remain as pressure and magnetic structure while emission dwindles. Brightness is not the same as influence. A relic can be dynamically important even when nearly invisible. The next visual anchor slows again. A large arc appears far from the center. The arc is faint. It is broad. Its curvature suggests it once belonged to a larger lobe. Inside the arc, the glow is slightly enhanced. Outside, the background is smoother. The arc resembles a quiet shoreline. It marks where a bubble once pressed outward. A payoff lands. Such arcs can be remnants of shocks or compression fronts driven earlier. Even a weak compression can organize magnetic fields. Ordered fields can enhance synchrotron emission along a rim. This makes boundaries easier to see than interiors. The relic then appears as an outline rather than a filled shape. Another scale shift arrives gently. A single active episode can last a short fraction of a lobe's lifetime. Many episodes can stack their relics. Over hundreds of millions of years, a region can accumulate layered bubbles. These layers can overlap and merge. The environment becomes a palimpsest of old cavities. The next payoff clarifies what layering implies. If a new jet turns on inside an old cocoon, it can travel farther with less resistance. The cocoon is lower density than the surrounding medium. This can produce longer jets and more distant hotspots. If the new jet points elsewhere, it can inflate a fresh bubble in a new direction. The relic field then becomes a backdrop. It shapes the next chapter without brightening itself. Another visual anchor appears in the transition between old and new. A faint relic lobe surrounds a narrower, brighter inner structure. The inner structure is misaligned. The mismatch suggests an axis change. The old boundary remains as a dim oval. The new channel cuts through as a straighter line. The contrast is calm and instructive. A payoff follows. The presence of a relic can explain why some systems show rapid changes in morphology. The medium inside the relic differs from the medium outside. The jet interacts differently with each. The environment is not uniform. It has memory. Another limit of observation appears with care. Misalignment can also arise from external flows that bend the jet. Old boundaries can be confused with unrelated background structure. Without full spectral coverage, relic identification can be uncertain. Yet a combination of morphology and spectral steepening strengthens the case. A gentle closing visual anchor settles the scene. The relic lobe drifts outward. Its rim becomes smoother. Its interior becomes quieter. The background glow resumes a simple gradient. The system looks less like a bright event and more like a long-lived weather pattern in plasma. A final payoff lands softly. Relic lobes show that jet energy persists beyond visibility. They provide the missing half of the story. They connect active beams to long-term environmental shaping. The closing sentences turn toward what follows without sharp suspense. As relics fade their remaining pressure and fields continue to guide later outflows. The next step gathers these threads and moves toward a gentle resolution of the overall arc. A jet can leave a signature that outlives its brightest phase by changing what the surrounding gas becomes. In that region, long-term consequences appear as mixed layers, transported material and altered pathways for cooling. The first scene is a vast dim halo that fades into a broader filament of gas. The filament is a faint bridge between galaxies. It is not uniform. It has knots where density rises. It has lanes where glow thins. Along one side, an old bubble drifts outward. Its boundary is marked by a soft rim. The rim is not a circle now. It is stretched into an oval. Its edge shows a gentle corrugation. The corrugation looks like slow waves along a shoreline. A small unlock arrives early. Jet influence persists through redistribution rather than permanent illumination. Dense gas can be lifted. Thin gas can be displaced. Old plasma can mix into new regions. The main concepts stay few. Entrainment is one. Entrainment means a jet drags surrounding gas along with it. Mixing is another. Mixing means layers blend and share heat and material. The third concept is enrichment. Enrichment means heavier elements spread into larger volumes of gas. Entrainment means a fast flow pulls in nearby material as it moves. A clear example follows in calm imagery. A narrow stream can pick up leaves from a surface. The stream remains narrow. The trail of carried leaves becomes wide downstream. The why matters in the same gentle breath. Carried material changes where cooling and condensation are possible later. The next visual anchor slows the pacing. Along the bubble boundary, a thin sheath forms. The sheath is brighter than the surrounding glow. It is a compressed layer with a sharper gradient. Inside the sheath, the relic plasma remains faint. Outside the sheath, the ambient gas looks smoother. Between them, a narrow band shows a wavy pattern. The pattern suggests shear. It suggests that two layers slide past each other, a payoff settles in place. Boundaries are not only edges, they are mixing zones where heat and material exchange. Even slow mixing can matter when time is long. Another scene appears farther along the filament. A faint plume extends behind the bubble. The plume is broader than the original jet path. It looks like a soft fan. Within the fan, brightness is mottled. Small patches form a chain. The chain bends gently with the larger filament. A payoff arrives from this chain. Entrainment can carry denser clumps outward. Those clumps can later seed local cooling if conditions allow. The motion is not a simple outflow that disappears. It becomes part of the filament structure. The main number arrives softly. A bubble can drift about 300,000 light-years before fading into the background, like crossing the span between distant city lights on a clear horizon. This distance is large compared with a galaxy core. It is small compared with a cluster scale. The scale shift is calm. Near the engine, changes can occur on timescales shorter than a year. Along the drifting bubble, changes unfold over millions of years. Along the filament, the consequences can persist for hundreds of millions of years. Another visual anchor slows the rhythm again. A long filament of cooler gas hangs beneath the bubble wake. The filament is thin. It is slightly brighter along one edge. It curves as if stretched by gentle flow. Small clumps dot its length. The clumps are not evenly spaced. Some are larger, some are barely visible. A payoff arrives. Mixing can both suppress and promote cooling. Heating raises entropy and delays condensation in the core. Uplift and expansion can allow localized cooling in filaments. The outcome is a landscape of patches rather than a single state. Enrichment adds another layer of quiet consequence. Heavier elements increase radiative efficiency in many conditions. Spread those elements widely, and cooling properties change in a distributed way. The bubble and its wake can transport enriched gas outward. Later mixing can bring some of that gas back inward. A payoff settles in place. The jet can move not only energy, but also the ingredients that set future cooling rates. The physical details remain concrete. The wake shows a smoother brightness gradient than the surrounding halo. The boundary shows a thin rim. The rim shows faint scallops. The filament shows a braided texture. The braided texture hints at magnetic threads guiding the plasma. The threads do not need to be strong to matter. They can organize motion and suppress mixing across some directions. A limit of observation enters softly. Enrichment is often inferred from subtle spectral features in faint light. Those features are weak. They can be blended by projection. Front and back layers overlap. A signal would combine multiple temperature phases into one average. This makes abundance estimates uncertain. Mixing rates are also inferred indirectly. They are reconstructed from morphology and from how sharp edges remain. True three-dimensional shapes are hidden, yet certain patterns are robust. Long-lived sharp rims suggest limited mixing across the boundary. Broad mottled wakes suggest mixing along the flow. Another limit of intuition follows. It is tempting to imagine mixing as a steady blur. In stratified plasma, mixing can be directional. Layers can slide while remaining distinct. A thin boundary can persist for a long time. A boundary can still exchange heat slowly. The result is gradual change rather than sudden homogenization. Another visual anchor arrives as the bubble reaches a denser knot in the filament. The knot brightens slightly. The bubble edge deforms. The oval rim flattens on one side. The wake broadens. A faint arc appears ahead of the bubble. The arc is a gentle compression front. It is not a sharp shock. It is a soft brightness in its enhancement. A payoff lands with this encounter. Environment shapes the fate of jet material. A bubble can rise cleanly in a smooth medium. In a structured filament, it can be shredded into patches. Those patches spread magnetic fields and particles over a wider region. The jet influence becomes more diffuse. It becomes easier to miss. It becomes harder to erase. The scale shift widens once more. Over tens of millions of years, a bubble can travel and deform. Over hundreds of millions of years, many such episodes can build a broad region of altered plasma. The region is not uniformly heated. It is patterned by wakes, rims, and filaments. This patterned structure changes future feedback. It changes where new jets propagate. It changes where cavities rise. It changes which regions cool into denser phases. Another payoff settles in place. The jet and the environment co-author the next chapter. The jet deposits energy and material. The environment redirects and stores that deposit. The result is a long-lived memory and gas structure. The closing visual anchor slows toward rest. The filament stretches into darkness. The old bubble becomes barely visible. Its rim softens. Its wake blends into the background. The halo returns to a gentle gradient. The consequences remain as subtle differences in texture rather than bright features. The final sentences turn toward a soft resolution. The jet story becomes a story of persistence through quiet redistribution. The next step gathers the arc into a calm synthesis and eases into a gentle landing. A jet is a narrow beam in space, yet its deepest story is how order appears from extreme conditions and then fades into quiet structure. In that region, relativistic jets are best understood as steady channels of energy and magnetic patterning rather than dramatic flashes. The opening scene is calm and wide. A distant galaxy core sits as a faint glow. From that glow, two elongated lobes extend in opposite directions. The lobes are dim and broad. Their edges show soft rims. The rims are slightly brighter than the interiors. Between core and lobe, the path is not a straight line of light. It is a gently curving corridor with faint knots. The knots are spaced irregularly. Their brightness tapers with distance. A small unlock arrives early. Narrow beams stay narrow because magnetic structure guides the flow and preserves direction over immense scales. The core concepts remain few. Collimation is one. Collimation means a flow is confined into a narrow channel. Magnetization is another. Magnetization means fields carry significant energy in the plasma. The third concept is beaming. Beaming means emission concentrates along the direction of motion. Collimation means the outflow keeps a small opening angle. A simple example follows. A stream of water through a smooth nozzle stays coherent. It spreads slowly compared with a spray. The why matters in the same calm breath. A narrow jet can reach far before dispersing. That reach links a compact engine to a vast environment. The next visual anchor slows the pacing. Along the jet corridor, a thin spine appears. Around the spine, a faint sheath widens like a soft cone. The spine is brighter. The sheath is dimmer. The boundary between them is a gradient rather than a wall. At the end, the jet does not stop abruptly. It terminates in a broader region where brightness blooms. That region blends into the lobe. The lobe edge forms an oval outline. Its rim has gentle scallops. Its interior contains faint filaments that curve. A payoff settles in place. The visible structure encodes the unseen balance between pressure fields and flow. A bright spine suggests a region of stronger particle acceleration. A faint sheath suggests slower or more mixed plasma. A rim suggests compression at a boundary. Another payoff follows soon. Beaming can make one side appear brighter even when power is similar. Motion aims emission forward. Geometry then becomes part of what is observed. This explains asymmetry without requiring a different engine. A gentle scale shift enters. Near the launching region, distances are small and change can be rapid. Far from the core, the lobe spans hundreds of thousands of light years. The same outflow connects both. The same field patterns can persist while details evolve. The main number arrives softly. A jet can remain collimated for about 100,000 light years like a lighthouse beam, crossing a vast sea before its edges soften. The comparison stays everyday and quiet. The number is a guide, not a precise limit. A visual anchor appears within this reach. The jet corridor shows faint bends. The bends are smooth. They suggest slow steering by external pressure gradients. The corridor also shows brighter knots. Each knot is slightly broader than the spine. Each knot fades downstream into the sheath. A payoff lands. Knots can mark internal compressions where flow adjusts to changing conditions. Each adjustment converts some directed energy into particles and radiation. The jet remains the same phenomenon. It simply breathes through checkpoints. A limit of observation enters softly. The launching region is too small and too distant to be resolved directly in most cases. Magnetic field geometry is inferred from polarization patterns. Those patterns can be diluted by turbulence and by mixed layers. A signal would average over many unresolved strands. This can hide ordered structure. Beaming adds another uncertainty. True speed and angle are intertwined in what is observed. Small changes in angle can mimic large changes in intrinsic power. Yet the broad conclusions remain steady. Collimation is real, magnetization plays a central role, beaming shapes appearance, another limit of intuition follows. The mind expects a jet to be a rigid rod of light. In plasma, a jet is a dynamic channel. It can contain a faster core and slower edges. It can carry energy in fields that are not bright by themselves. Brightness is a tracer of where particles radiate, not a map of all power. A payoff settles in place. This distinction explains why jets can do work on environments even when parts are faint. The next visual anchor returns to the lobes. The lobe interior is mottled. Filaments arc like soft brushstrokes. A cavity appears as a darker region within the glow. The cavity is not empty. It is lower density plasma with different field structure. The cavity boundary is marked by a rim. The rim is a thin layer where density and field align. A payoff follows. Lobes are not mere leftovers. They are reservoirs that store energy and release it slowly. They lift gas. They compress gas. They seed mixing. Over long spans, they regulate how the surrounding medium cools and circulates. The scale shift widens again. Over millions of years, a jet episode inflates lobes. Over tens of millions of years, lobes fade by radiation and expansion. Over hundreds of millions of years, repeated episodes create layered cavities and enriched wakes. The system becomes a memory field in plasma. A fresh analogy appears and stays unique. A river delta builds land grain by grain. Each flood is brief. The shoreline change lasts far longer. In that region, each jet episode is a flood of energy. The lobes and cavities are the shoreline change. The environment records cumulative influence. Another payoff lands. This cumulative record explains why jets matter for large-scale structure. They are not only bright events, they are long-term sculptors of pressure and entropy distribution. They leave gradients. They leave boundaries. They leave pathways that guide later flows. The closing visual anchor slows toward rest. The scene pulls back farther. The galaxy becomes a faint point. The lobes become a subtle elongation. The surrounding medium becomes a smooth field with gentle texture. The jet corridor is no longer a line. It is a whisper of direction. The last payoff arrives softly. Relativistic jets show how narrow order can arise, propagate, and then dissolve into quiet structure without vanishing. The final transition settles without opening a new question. The remaining glow becomes a steady background. The story resolves into a calm continuity of fields, motion, and time.